Hello and welcome to another Stephen Mendes video. In this video, we are going to show you how to implement a function using a decoder or a multiplexer. When using a decoder to implement a function, it's the perfect thing because we have the A, B, and C, and we have the 8 rows coming out as the 8 outputs of our 3x8 decoder. There are two types of decoder. One is the normal decoder and the other is the active low decoder. Notice that when you're asked to do an active low decoder, you must put the circles on the outputs because active low means we're inverting all the outputs. So let us see now what happens. Once again, we slow it down to show you what happens in a decoder. Let us put in 101. We know that that is 5. The 5 line is going to have a 1 on it, and all the other outputs are going to be 0. That shows we have selected 5. We're going to put in 3 on the active low decoder. And now we see that in fact the 3 line is a 0. So it's easy to see from this diagram that with the normal decoder, the particular output becomes a 1 when the input selects it. And in the case of the active low decoder, the particular selected output, in this case 3, has gone to a 0. So we see that the outputs are mostly 1s for active low and 0s for the normal decoder. Okay, so let us now put some functions on them. That's what we want to do now. We're going to put a function. What happens is, as you can see there, we have to use the appropriate gate to connect the rows to get what we want. So we have sum of products on the left, where the particular numbers are actually going to produce a 1. In other words, we will get a 1 on 0, a 1 on 4, and a 1 on 6 in terms of the row numbers for that particular function shown. Now on the right side, because this is active low, we have to use an AND gate. We cannot possibly use an OR gate, and a single 0 will block the gate. Therefore, if there's a 0 on 1, a 0 on 3, a 0 on 4, or a 0 on 5, we will get a 0 at F. Now let us go on to implementing functions with the multiplexer. There we have a function and we've put it on the truth table in the normal way. Now whenever you draw your 4x1 multiplexer, you're going to draw it as shown. It has 4 inputs, 2 select lines, 1 output line, and do not forget to put on the B, C, and the F. The F is the output of the function, and the B and C are applied to the select lines. The B must go to the 1, and the C must go to the 0. Why? Because the B is the more significant bit than the C, and the 0 is the least significant bit of your select lines. Now notice we haven't mentioned the A. What do we do with the A? Well, we draw a little diagram to decide what we're going to do with the A. There it is. Now once again, you don't have to do this in slow motion because this diagram is drawn the same way all the time. The same way all the time, just like how you draw the Carnot maps. Make sure that you have the A bar as the first row and the second row as the A, because only when you have the rows A will you get 4, 5, 6, and 7. Otherwise, on A bar with A as a 0, you get 0, 1, 2, and 3. So you have to just do them all the same way, having the lower numbers on the A bar and the higher numbers on the A. Now in this case, it has 4 inputs. If you had an 8 input, you would have B, C, and D, but you would still have an A bar row and a row. So it's always the most significant bit, whether it's 3 bits or 4 bits, that you put on these 2 rows, and you would have to use an 8x1 multiplexer if you had a 4 variable function in A, B, C, and D. Okay, now this is the part that we're going to do in slow motion. We're going to pick off the ones of the function. Notice that I've marked them there. And we are going to circle the ones of the function in our table below. It's running a little slow. Maybe I could speed it up for you slightly. Let's see if we can do that. There we go. No, it's not quite so painful. Okay, so we're going to circle the ones in this particular case, because this is, there we go, we've circled all the ones that are ones. Now let me explain what is going on here at the very bottom. If we have a circle only on the A in any one column, then that column is an A. If both of the rows in the column are circled, then that column has a 1. If only the A bar row has the circle in any particular column, then that column is A bar. And if the column has in nothing circled at all, then that column is 0. Got it? Okay. The last thing we have to do now then is to connect input 0, notice the column of input 0 is going to A, and the other columns are going to be connected to A bar, 0, and 1. So let's see that happen quickly now here, and then we are finished. Now, this multiplexer is a normal multiplexer. What we might want to do is we might want to try it with an inverting multiplexer. Okay, so here's another function, and we're going to implement this function with an inverting multiplexer. Notice the inversion circle. Do not forget that circle on the output of your multiplexer. Everything else is the same as it was in the previous diagram, except that we have a circle on the output. Now we need our little table, which looks exactly the same as it did before. We have the A bar row, we have the A row going from 0 to 3, and the A row going from 4 to 7, and they coincide with 0, 1, 2, and 3, which the top row is really the inputs, 0, 1, 2, and 3 of our multiplexer. Now we're going to do it in slow motion, but we'll make it a little quicker so it won't be quite so painful. We are going to mark off the rows as zeros, and we're going to circle the zeros in our table. Okay? We circle the ones if it's a normal multiplexer. We circle the zeros if it is an inverting multiplexer. So quick as a bunny, we are going to circle those zeros there. And once again, if we have a circle in the A row, we get A. If we have a circle in all 2 rows, we get, in the same column, we get a 1. If there's no circles in the column, we get a 0. And if the A bar row has the circle only, then we write A bar to the bottom. And finally, we connect the A1, 0, and A bar to the input, as shown. And we are done. Thank you so much for watching, and we'll see you in the next video.